Hi, I'm Mr. Miller, and this is a lesson on reciprocal, quotient, and Pythagorean identities. So first of all, let's look at the relationship between x, y, and r when we've got an angle in standard position here, and x and y are the x and y coordinates of this point, which is on the terminal arm of the angle theta in standard position, and of course r is the distance from the origin to that point. So the relationship between x, y, and r is a Pythagorean relationship, x squared plus y squared equals r squared, and it leads to these three Pythagorean identities. So first of all, if we take this equation and we divide all of the terms by x squared, we get 1 plus tan squared theta is equal to secant squared theta. Because don't forget that y over x is just tangent, r over x is the reciprocal of x over r. X over r is cosine, r over x is secant, so this is secant squared theta. So this is the relationship between tangent and secant, and it's called a Pythagorean identity because it came from this Pythagorean relationship. So we can get another identity like this if we take the original equation, we divide all the terms by y squared. In this case, we get cotangent squared theta plus 1 is equal to cosecant squared theta. And that's because x over y, which is the reciprocal of y over x is tangent, x over y is cotangent. Cotangent squared theta plus 1 is equal to r over y. Well, that's the reciprocal of y over r. Y over r is sine. Reciprocal of sine is cosecant. Cosecant squared theta. And finally, x squared plus y squared equals r squared. If we divide all three terms by r squared, then we get x over r is cosine, y over r is sine, and r over r, of course, is just 1. So cosine squared theta plus sine squared theta is equal to 1. So this is an algebraic proof of these three identities. And there are some other identities that are good to know. For instance, reciprocal identities. We know that cosecant is the reciprocal of sine. We've got r over y for cosecant. Sine is y over r, so cosecant is 1 over sine, and likewise, sine theta is 1 over cosecant theta. We've got that secant theta is r over x, and cosine theta is x over r. So secant theta is 1 over cosine theta, and cosine theta is 1 over secant theta. And finally, cotangent theta is x over y, whereas tangent theta is y over x. So cotangent theta is 1 over tangent theta, and tangent theta is 1 over cotangent theta. Now, quotient identities. If you take the tangent, which is y over x, and you divide the numerator and denominator by r, then you'll notice that y over r is sine theta and x over r is cosine theta. So tangent theta can be written as sine theta over cosine theta. And likewise, cotangent theta, which is x over y, if you divide the numerator and denominator by r, you get cosine theta over sine theta, which is a substitution that you can do for cotangent theta. All right, so now we've had three sets of identities: Pythagorean, reciprocal, quotient, and we've done all sort of algebraic proofs up to this point. Let's take a look at doing a proof numerically. So we've already seen that sine squared theta plus cosine squared theta is equal to 1, and that's for all theta. But let's see if we can prove it's true for a particular value, like theta is pi over 6. So what I would do is I would take the left-hand side of the equation and I would replace the theta with pi over 6. I would evaluate this by, first of all, looking at that angle pi over 6 and recognizing, okay, so that's a 30-degree angle, which is a special part of a special triangle, 30, 60, 90. Sides go 1, 2, root 3. I know that the sine of pi over 6 is going to be y over r, 1 over 2. and I'm going to take that sign and then I'm going to square it. Now for the cosine, I'm taking x over r root 3 over 2, and I'm going to square that. When I square each of those, I get 1/4 and I get 3/4. When I add them together, that gives me 1, which is identical to what we have in the right-hand side of the equation. So this proves to be true for the particular angle of pi over 6. And now if you wanted to prove that this identity holds on a whole set of, a whole domain of theta values, so for instance, for theta going from negative 360 to positive 360 degrees, or negative 2 pi to positive 2 pi, we could graph this. And if you put that into something like Desmos, then you would find that when you add them together, you get 1 for all of these theta values. And this is obviously pretty convincing that it's true for all values. The algebraic proof is ultimately the proof that it's true for all angle values. But you can see how it can start from, if you're exploring a particular angle and you find that something is true, you could explore graphically, is this always the case? And then of course you'd want to follow up with the algebraic one. So last thing, we're going to take a look at how we can use identities like these to do some simplification. So here we have sine theta times cotangent theta, and then we're also going to look at restrictions. So if we write the cotangent in terms of sine and cosine and simplify, this is what it would look like. We've got sine theta times cotangent theta, which is sine theta times cosine theta over sine theta. There's a common factor of sine theta that's going to divide out there, and we're left with just cosine theta. And this is the simplified version. So this is true for all theta. However, there are restrictions. And the restrictions are that sine theta is not allowed to be equal to 0. So we know that sine theta is going to be equal to 0 at multiples of pi, or integer multiples of pi. So that completes this lesson on reciprocal, quotient, and Pythagorean identities. Hopefully you understood that well, and thanks for watching. Have a good day. Bye.